Okay, so now let us go for next topic, next lecture. What is that? That is about the density of state function, density of state function in semiconductor crystal. Okay, so as we have seen in last class, that is what density of state function for free electron. Yes, free particle. Okay, so where mass is not effective and energy is also not get shifted by some amount, that energy is also same, means energy, and where energy and mass is not affected. Okay, so when you will go inside the semiconductor crystal, their mass will get affected. Thing is what accept effective mass and its energy that will get shifted by some amount. Okay, so that is only the difference. So now see the density of what today topic is density density of state density of state function in semiconductor semiconductor crystal. Okay, in semiconductor crystal. Okay, so now today we are going to see the density of state function in semiconductor crystal. Let us see. Now the difference is only what about the mass and somewhat energy that will get shifted by some amount in case of valence band and in conduction band. Okay, so first we will see the density of state function in conduction band. First in conduction band. In conduction band, we see, as we know very well, this is what energy versus momentum curve. Okay, for conduction band. Yes, where the electron is just what in case of conduction band, the electron in the conduction band, that is tending to settle down at the bottom of the conduction band. Yes or no? At the bottom of conduction band, all the electron is what is trying or tending, okay, or tending to settle down near the bottom of this conduction band. Okay, so bottom of this conduction band, and here in this bottom of conduction band, the energy of this electron near the bottom of the conduction band is what is approximated as parabolic curve. Yes, approximated as parabolic curve. This is not a parabolic curve. It is a sinusoidal function. What is this? This is a wave function. What wave function? Yes, here electron is behaving like a particle. No, the particle is behaving like a wave. Okay, so wave particle duality principle. Okay, so this is what my wave function. Okay, wave function corresponding to what? Corresponding to allowed energy band. Yes, so this is not parabolic. So this is what energy, the energy of this what electron, which is settled down at the bottom of conduction band. Okay, so the energy of this electron is approximated as what? Parabola. Okay, parabola whose equation is given as what? E minus ec. E minus ec is equal to what? E minus ec is equal to h cut square k square divided by what? 2m, divided by 2m. Yes, 2m. So this is what the energy. Yes, this is what the energy. Yes, energy or momentum relation in case of what? Conduction band. Yes, now if you see the density of what? Density of allowed quantum state. Density of allowed quantum state in conduction band is what? See here we are assuming here also similar case like that we have assumed for the free particle, like three-dimensional infinite potential band. We are also assuming in case of conduction band. Okay, so conduction band we are also assuming the three-dimensional infinite potential band. So therefore here everything is same except this energy and mass that will get affected. Okay, here energy this will get shifted by some amount. Okay, so this energy will get shifted by some amount and this mass will get affected. Okay, so this is what this mass will get affected and this mass in the conduction band is what effective mass, which is a positive. Okay, the positive mass, positive what, positive effective mass of electron in the conduction band, that is what, positive. Yes, so therefore here this mass is what, mn star, mn star. Okay, so this mass is mn star, this is what effective mass. Now similarly, if we see directly the density of allowed quantum state, density of allowed density of allowed quantum state in case of conduction band, that is equal to, that is equal to what, that is equal to 4 pi to mn star. Okay, so this is my effective mass of electron where in conduction band, to the power 3 by 2 divided by h cube. Yes, divided by h cube, not h cut, h cube into square root of what, square root of e minus ec, square root of e minus ec. So this is what, this is the what, this is the density of allowed quantum state or density of discrete energy state, discrete energy state where in conduction band, in conduction band. Okay, so in conduction band where only the difference is that only the energy that energy got shifted by some amount and this mass get affected, energy get shifted by some amount and this mass get affected by what, the affected by some internal force. Okay, so that is existing inside the crystal. Okay, so here due to which the movement of particle inside the what, inside the semiconductor crystal is different from the movement of particle outside the crystal. Okay, so due to which the mass, okay, so this mass will get affected. Okay, so mass of what, electron inside the semiconductor, that will get affected because of what, because there exists an internal force with an external force. That internal force is existing what, because of electric force that exists, electric force that what, electric force that is existing between what, between positive particle. Okay, so positive ion or you can say proton or negative electron, which will influence the what, influence the motion of electron inside the crystal. Okay, so due to which its mass will get affected, which is represented by mn positive, and this mass is what, effective, this effective mass is positive. Okay, so this is only the change that we get in case of allowed quantum state, allowed density of quantum state. Okay, allowed density of quantum state or allowed density of discrete energy state. Okay, so this is for conduction band. Yes, conduction band, density of allowed quantum state. Yes, this is very important because from here we are able to calculate what, we are able to calculate the number of electron and hole concentration. Yes, from here we can calculate what, number of electron concentration. So this is for what, conduction band. Yes, conduction band, density of allowed quantum state or density of discrete energy state in conduction band. Okay, so in conduction band. So now we will see for what, now we will see density of what, density of allowed quantum state or density of discrete energy state in valence band. In valence band, see here, valence band, in valence band, in valence band, if you see in valence band, see valence band, as you know very well, for valence band, for valence band, energy versus momentum curve is what, this is something like this. Okay, so this is not a parabolic, it's a sinusoidal curve. Okay, so this is nothing but wave function. What, wave function corresponding to what, wave function corresponding to allowed energy band. Yes, allowed energy band, this is what, energy versus momentum, and this momentum is not directly momentum but it is related to momentum, p by h cut. This p is what, momentum. Okay, so this is what related to this, and as you know very well, this k is what, this k is nothing but wave propagation vector, wave propagation vector. Okay, so this is nothing but wave propagation vector which is related to momentum for free particle. Okay, actually the k is representing what, k is representing the moment of crystal. If you see, the k is representing the moment of crystal. Okay, for particle it is what it is related to the particle, like k is equal to p by h cut. Okay, actually it is what wave propagation vector. Okay, as the wave is propagated in the three-dimensional space, that is what k vector space in three dimension. Okay, so for free particle it is related like this, k is equal to p by h cut. Okay, so this is what in case of valence band. Now here if we see all what the electron in case of valence band, see here, as we have seen that the effective mass of electron in case of valence band is what, negative. But here in case of valence band we are not going to calculate the concentration of, electron, but in valence band we want to determine what, we want to determine the concentration of hole. So therefore we only focus about hole. Okay, so hole, if you see in case of valence band in case of valence band, what, in case of valence band, all the hole, what, all the hole that will tends to what, that tends to accumulate. Okay, all the hole that tends to accumulate at the top of what, at the top of the valence band. Yes, at the top of valence band. So this is my what, valence band. Here in case of valence band, okay, inside the semiconductor, whatever the hole is there in the, in valence band, all will get what, all will tends to what, all will tends to accumulate at the, at what, at the uppermost level of valence band. Yes, uppermost level of valence band, all these holes are tending, yes, tending to settle down, or you can say tending to accumulate at the top of valence band. Yes, now the energy of that hole. Okay, so the energy of this particle, the energy of this particle as whole. Okay, the energy of this particle as whole can be approximated as what, approximated as parabola. What, parabola. So this is my parabola. Okay, so the equation for which is given by what, e is equal to what, if we see here, e is equal to ev. Okay, e is equal to ev minus h cut square k square divided by 2m, divided by 2m. Now see here, this will become ev minus e. ev minus e is equal to h cut square k square divided by 2m. Okay, where m is what, mass. This mass is nothing but effective mass. Effective mass of what, effective mass of hole. Yes, effective mass of hole. Now see this. Okay, so this is my effective mass of hole. Okay, so this ev minus e is equal to, ev minus e is equal to h cut square k square divided by 2mp star, where mp star is the effective mass of what, effective mass of hole in valence band. Similarly, if we see the effective mass of electron in case of valence band, that is negative, now this effective mass of hole is positive. Okay, everything we have explained, okay, in last class. Okay, whatever we have discussed so far in all the lecture. So you can just go on I section button, just click on that button, and you will see all the lecture, okay, related to this, all energy band formations and the effective mass of electron in conduction band and in valence band as well. Okay, so this is what all about the effective mass. Okay, so effective mass of hole in valence band. Now we are going to see the density of state function in semiconductor inside valence band. Okay, so density of allowed quantum state. These are what, density of allowed quantum state, or allowed discrete energy state. Okay, allowed discrete energy state which are lying between the allowed band. Yes, these discrete energy level are lying where, between allowed band. Okay, because allowed band is actually made up of what, allowed band is actually made up of discrete energy level. Okay, so discrete energy level everything we are confirmed about all these. Okay, all these fact whatever we have seen. Okay, until now. See here, now we are going to see what the density of allowed quantum state for what, for valence band. This is what gv of e. What, gv of e is equal to what, gv of e is equal to 4 pi into 2m p star to the power 3 by 2 divided by h cube into square root of ev minus e. Okay, so why, because in case of valence band we are, in case of valence band we are considering similar like what, similar like free particle case. What the free particle, here the free particle is what, hole. This hole we are assuming that it is inside the three dimensional infinite potential well. Okay, so everything is same, but the difference is that here the mass will get affected. Okay, and this energy will get somewhat shifted by some amount. Okay, in case of valence band inside the semiconductor crystal, everything is similar like free particle, in like the case of free particle. Okay, free particle, here also we are assuming what, we are assuming the three-dimensional infinite what potential value. Okay, so everything is same, and the difference only that this mass will get affected. Why? Because inside the crystal, movement of electron that is different from the movement of particle outside the crystal. Why the movement is different? Because here as we know to move, as we know for current, what for current the charge should be what, charge should be in motion. Yes, because the current is nothing but what, flow of charge carry. Yes, flow of charge carry, charge should be move. Okay, charge should move inside the crystal, so which will give rise to what, current. But this movement of charge is what, this is different from what, this is different, the movement of this particle is different. Okay, for this movement of particle, what we need to push this, we need some force. Okay, we need some force. For that force we are applying one external force with the help of what, by applying external agent as what, as voltage. Okay, so due to which what, electric field will get established. Okay, so that electric field will maintain what, this electric field maintain what, the movement of this all particle in one direction. Okay, so which will give us what, resultant current. But this movement of particle is what, somewhat different from the movement of particle in free space, or you can say the movement of particle in conductor. Yes, so why? Because here because here with this what, with this force, with this external force, there exists an internal force. Why? Why there exists an internal force? Why? Because inside the crystal, what is there, there is a energy band gap. Okay, there is a conduction band, there is a valence band. Okay, so there is a valence band. Now this electron is moving where, in conduction band, in a random direction. Okay, so therefore we want to what, we want the movement of this particle in such a way that it should move in one particular direction. For that, what we need, we need one external force. Yes, we need one external force, so that there is an establishment of electric field. Okay, so that electric field maintain the force, maintain the movement of these all electron in one particular direction. Okay, so but this movement of particle will get affected by what, by another force, because there exists another force inside this crystal. Why? Because there is a valence band. Okay, so in valence band there is what, hole, there is a hole, and there is a bound electron also. Okay, hole means there is a positive charge, hole means there is a positive charge, bound electron means this is electron has negative charge. Wherever there is a positive negative charge, there is a force of attraction or not? Yes, there is a force of attraction. So therefore, if there is a force of attraction, means there is an electric force, there is an electric force. Yes, this is my electric force, this is my electric force of attraction between this electron, positive and negative charge, and which will definitely influence or affect the motion of this particle. Particle means the motion of this electron in conduction band. In conduction band, in the sense that the motion of particle in interatomic space inside the crystal, that will get affected because of this internal force. This internal force is what, electric force, which will affect the mass of this what, particle. So therefore this mass is nothing but effective mass. Okay, so this mass is nothing but effective mass. This is only the difference that we have found in case of what, in case of semiconductor crystal. Okay, so whenever the particle exists inside the crystal. Okay, so this is only the difference between what, the particle in free space and the particle inside the semiconductor crystal. Okay, so we are confirmed now all about the particle in free space and particle inside the semiconductor crystal. Okay, so we have seen in both cases, in conduction band and in valence band. Yes, in valence band, what, the effective mass of hole is what, positive, but the effective mass of electron in the valence band is what, negative. Okay, so we are not considering this there, we are not considering the effective mass of electron here in valence band, because our main target is what, to calculate the concentration of hole. Okay, for that what we need only the effective mass of what, hole inside the what, inside valence band. Yes, so For that everything is same for the density of state function. Yes, density of state function in the sense means what we are going to calculate, we are just calculating the density of allowed quantum state. What are these allowed quantum state? These are nothing more than that of what discrete allowed energy state that exist, what that exist where in the allowed energy band. Yes, what are those allowed energy band? Because you know very well, during the formation of what crystal, whenever there is a formation of crystal or solid, the discrete energy level, okay, so this discrete energy level that will get split into allowed energy band and forbidden band, okay. So therefore this allowed band is actually made up of what? Actually made up of discrete energy level, okay. So where this discrete energy state is nothing but it is the house of what? Electron, house of particle. Particle where is sitting the particle? Particle exactly sitting one where in discrete energy state. Okay, so that is the main purpose that we want to find. What we want to find the density of allowed quantum state. How many number of density of allowed quantum state is there? That many number of electron, either electrons or hole, are present inside the semiconductor crystal. Okay, so once we are able to calculate all these concentration of electrons and hole, then we are able to calculate the current. Okay, we are able to calculate the current, and we will reach, therefore at the end we are able to reach in our main ultimate goal, that is what? That is to determine the electrical characteristic of semiconductor device. Okay, so that's all for what this discussion of what density of state function in semiconductor. Why it is important now we have seen. Okay, so what is because it is main root cause. Okay, it is the main root cause for everything whatever you are going to see inside the device. Okay, inside the device we are just playing with the device by changing its property. Okay, by changing its property means by changing its current. Okay, for current what is needed? Flow of charge carrier is needed. Okay, so for flow of charge carrier needed, what we need for that? Number of electrons and hole concentration, which is available in semiconductor for conduction process. Okay, so therefore these number of charge carried are the function of what? Are the function of what? Are the function of discrete, are the function of energy level or quantum state. Okay, so that is the reason that we are that is the reason that we are what? Determining the density of quantum state or density of allowed quantum state in both conduction band as well as valence band, because the current may be due to hole, and the current may be due to what? Or due to allowed electron, it may be due to allowed hole, and it may be due to both electrons and hole. Okay, depending on which type of semiconductor it is. Maybe it is positive, maybe it is p-type semiconductor, or it may be n-type semiconductor, or it may be intrinsic type semiconductor, or pure semiconductor where there is no doping. Okay, so this is all about what? Density of state. Okay, so this lecture we will end here. Okay, so now then next we will start our discussion what? Semiconductor in thermal equilibrium. Okay, so this is all about what? Density of state function. Okay, inside semiconductor crystal. What we have completed density of state for valence band and conduction band. Okay, so valence band and conduction band that we have completed both. Now we will see the comparison between these two, density of state in conduction band and valence band. See the graph. Okay, so both diagram for the density of function in conduction band as well as in valence band. See that we have calculated, this is the density of state function for conduction band. Okay, so density of state in conduction band, this is what 4 pi, yes, into 2mn star to the power what? 3 by 2 divided by h cube. Yes, h cube into square root of e minus ec. Okay, so this is the density of state function. Yes, density of state, where density of state in conduction band. Yes, these are density of state. Yes, density of state in conduction band. Yes, density of state in conduction band. Now you see here the density of state in valence band. See Gb of E. What is this? Density of state. Where density of state in valence band 4 pi into 2m P star. What is this? Effective mass of hole. Where? In valence band. Divided by H what Q. Okay, into square root of EV minus E. Yes, EV minus E. So this is my density of what? Density of a state. Density of state in where? Density of state in valence band. Density of density of state. Density of state in valence band. Density of state in valence band. Yes, density of state in conduction band. Now we are going to what? We are going to draw what? The characteristic between energy and density of state. Yes, energy. Whose energy? Particle energy. Either it is electrons or hole. In case of conduction, it is electron as a particle, and in case of valence band, there is a hole as particle. Okay, so we are going to draw the characteristic between the energy of the particle and the density of state. Okay, so what are those density of state? This is nothing but it is a density of allowed quantum state or allowed discrete energy state. Okay, so now we are going to draw this graph. Okay, so draw this characteristic between what? Draw the characteristic between energy and density of state. See, first of all, if you see this, first you see GC of what? GC of E. Okay, so GC of E is equal to, let us take it as a constant because 4 pi is constant. Effective mass of electron is also constant. Planck's constant, this also a constant. Okay, so all this factor is what? All this factor is constant. Take it as k. Okay, take it as k. Now square root of what? Square root of E minus EC. Yes, EC is also constant. Now what you do? Just square on both sides. GC square of E is equal to k square into k square into E minus EC. Okay, so now see here, E minus EC is equal to what? GC square E divided by what? Divided by k square. Yes, k square. Now see here, E minus EC. E minus EC is equal to, let us say this, E is equal to what? E is equal to, when it will come this side, this become EC plus what? GC square divided by k square. Yes or no? So this is what? My energy. Yes, energy of what? Free particle. Energy of electron as a particle. Where? In conduction band. Yes, where? In conduction band. Now see for hole, similarly for hole what is here? If you see for hole, it will come like, it will come E is equal to EV. What? EV minus, but in case of plus it is minus because it is E minus EV. Okay, so EV minus GV square of E. GV square of E. Okay, so GV square of E divided by K square. Okay, so where K, here K is what? K is different. Here K is different. So it is K C and this is my KB. Let us take this as C. KC. Okay, so this number is KC and this is my KB. Yes, so these are two equation. These are two what? Two equation. Okay, so with respect to see energy, this is density of state and energy relation equation. Why we are writing like this? In order to draw the characteristic between what? Energy and density of state in both conduction band and valence band. Okay, so these are the main density function in conduction band and in valence band. Okay, so these are what? Relation. We are making this perfect relation because we want to what? We want to draw the characteristic between what? Energy and density function. Energy and density function, or density function of what? Allowed quantum state or allowed discrete energy state. Okay, in both conduction band and in valence band. Okay, so just note down it. Okay, so then I am going to rub it, then after that we will draw the characteristic. Okay, between energy and density of quantum state. So let us see. So this is not 9, this is G, just G. Okay, so let us see here. So now see the characteristic graph between energy and between what? Between energy and density of a allowed quantum state for For both simultaneously we will draw for both conduction band and valence band. See here, graph. This is what characteristic graph. So let us write this characteristic graph. Characteristic characteristic just wait. Characteristic graph. Characteristic characteristic graph between between energy between energy between particle energy of particle. Yes, like particle like electron particle like electron and hole, and density density of allowed quantum state, density of allowed quantum state or allowed discrete energy state. Okay, so this is what characteristic graph. We are going to draw what characteristic graph. Okay, so characteristic graph between energy of particle and energy of particle like electrons and hole. Electron in case of conduction band and hole as a particle in valence band. Okay, and density of allowed quantum state. This is a density of function, in the sense the density of allowed quantum state or allowed discrete energy state. Okay, so we are now drawing this characteristic graph. Okay, between this energy and density of quantum state. Now see, density of quantum state. This is for conduction band, this is for valence band. Okay, so conduction band and valence band. Now let us write this equation here separately. This is for energy in case of conduction band, EC plus GC square of E divided by KC square. Okay, so this, and another for valence band it is EV minus GV square of E divided by KV square. Okay, KV square. So this is for conduction band. Yes, this is in conduction band, and this is for valence band. Yes, now see here, just draw the energy versus density of state graph. See, characteristic graph. So this is my density of, see, this is my energy axis, and this is my density of state, G of E. Okay, so G of E. So this is my energy versus density of state graph. Okay, so now you see here, if we draw this graph for what, let's say for valence band. Okay, in case of hole, when we take the hole as a particle, in that case the density of state function in valence band is what? See, let us assume that it is a constant. Okay, so this is constant, this is also constant. Okay, so when we see this graph, when GB of E is equal to 0, when the density of state is equal to 0, then this E is equal to what? EV. Then this E is equal to EV. Yes, E is equal to EV. Let us say somewhere here, E is equal to EV. Yes, E is equal to EV. Now when this density of state start increasing, then what happens? So this start increasing like this, and the point will come when this is equal to EV. Okay, and E is equal to, and when this when this total function become equal to EV, then it is approaching toward what? Zero. Toward zero or not? Toward zero. So this is what? This is equation like, see, E is equal to what? E is equal to like EV minus x square divided by some constant kb square. Okay, this is the equation. This is some equation like this. Okay, so when you will draw this equation, you will get like this curve. Okay, so like this, and then it will approach to zero. Okay, so when this factor will become is equal to ev, and it will start approaching toward what? Zero axis. Yes, when this gv of e increasing. Okay, so this gv of e is increasing. See here, this. So now similarly for conduction band, when this density of state is zero, then E is equal to ec, but this ec is above ev. Yes, above ev. Yes or no? Above ev. So when this function will become equal to ec, this is never going to zero. Yes, because it is plus sign. So when when this function will exceed this energy level, then it will go above. It will approach toward infinity. Yes, it will approach like this. This. So this is the graph between density of graph between what? Density of quantum state and energy of what? Particle. Energy of particle. See this one. This is for valence band. Yes, and here at when density of state is zero, then my energy of particle is EC. Yes, EC, and this gap is what? EG. Yes, EG, which is nothing but EC minus EV. Yes, EC minus EV. And here, if you see, there what? The density of quantum state G of E is what? Zero. Yes, in this gap density of quantum state is zero, and here if you see this is nothing but density of quantum state in conduction band, gc of e. Yes, gc of e, and this is for what? Gc, gv, gv of e. This is what? Density of quantum state in valence band. Yes, this is for conduction band. Yes, this one for conduction band. If you see for this is what? For valence band. Valence band. Yes. So these are two simultaneous characteristic between the energy and density of state. Yes, energy and density of state. As if you see in case of valence band, yes, it is because of this negative sign. It is approaching toward what? It is approaching toward means zero. Okay, so when it become what? When this factor will become equal to ev, at that time it become zero. Yes, it become zero means it will extend toward negative. Okay, when this will exceed this, it will go toward negative, minus infinite side. Okay, so minus infinite side. When this factor will exceed this, it will go plus infinity. Okay, plus infinite side. Okay, so this energy of particle will extend up to plus infinity when this factor will increase. Okay, exceed this what? This edge of the conduction band. And in case of valence band, when this density of quantum state, okay, exceed this what? Edge of the valence band, then this energy of the particle will extend toward minus infinity, minus infinite. Okay, so this is what the simultaneous characteristic for both conduction band as well as for valence band, between what? Between energy of particle and density of quantum state. Okay, so this is all about this lecture about density of quantum state. Okay, so thank you very much. Okay, so we will meet in the next lecture. Okay, so that is about, I think, so that is about semiconductor in thermal equilibrium. Okay, so this is all about the density of quantum, means density of state function. Okay, so this is graph between energy and density of quantum state. Okay, simultaneously for both conduction band and valence band. Okay, so this is the energy band gap. Okay, so energy band gap. Okay, where there does not exist any around quantum state. So therefore, the density of state function is 0. Okay, so within this forbidden energy band. Okay, thank you very much.